Okay. Are there any outstanding questions that I can answer? No? Okay. All right, so at the end of the last lecture, we introduced the inner product, and that is going to be where our focus is going to turn. And hopefully, with the inner product defined on functions, as opposed to just, an array of numbers, and the convenience of working in an orthonormal basis, this is an idea that we're going to develop in detail. So in the next block of material, not what we're about to do, but the block beyond that, which is on Hilbert spaces, you're going to see a lot of what you've probably used before in terms of vector spaces built out of functions. So Fourier modes, Legendre polynomials, Bessel functions, etc. These are all just vector spaces which are constructed out of functions. But one of the important ideas in there is constructing or finding an orthonormal basis with which to work. So one of the things to realize if you're going to start extending this to functions in general is that you have to let the dimensionality of the vector space go to infinity. And a simple way to see that is if we take the polynomial spaces we've been working with as an example, P2, P3, whatever. You can always write down a vector which is representative of an element of the set, P3. So you got a constant, a linear term, a quadratic term, and a cubic term. But could you write down a vector that corresponds to, in some strange way, e to the t? Can you do that? Can you do it if the dimensionality of the space is extended to infinity? Yes, you can. It's just a Taylor series of e to the t. Okay? And this is the story in general. If you want to work with just general functions, you have to extend it to infinity. So we're going to be doing that in due time, but we're not going to start it today. Rather, we're going to continue our analysis of the inner product. And we're going to explore some of the features that we explored for vector spaces in general and see how the inner product brings change to the story. So let's get back to developing inner products in general. Okay, so we'll start with the definition. In a finite dimensional space, and of course I mean vector space when I say space, an orthonormal set is complete if it is not contained in any larger orthonormal set. Okay? That's a definition. Okay, we got Sam and we got Ross on. Good. All right. Okay. So hopefully this should make some sense, and we'll revisit this in a moment with some examples. So let me go ahead and write down a theorem which is a result of this. Okay, an orthonormal set and remember, when I talk about an orthonormal set, I'm just referring to something like this. Where you've got a set of basis vectors, and they are orthogonal to each other. That's all I'm talking about. An orthonormal set is linearly independent though not the reverse. sentence provides a basis and a complete one if it's complete. Okay? This is of course a theorem. All right. Now, interesting. What is the though not the reverse? What am I implying with it? Oh yeah, you got a question?
No, not all linearly independent sets are orthonormal. Right?
Exactly, exactly. But what this is stating is that an orthonormal set is automatically linearly independent. Okay, we clear on that? Okay. So let's just check out a quick proof. Recall how we stated whether a set of vectors is linearly independent or not. If the sum over I of alpha I xi equals 0 implies that all of the coefficients are 0, then the set of xi is linearly independent. Okay? Now that's just that's our earlier recognition of identifying if a set is linearly independent or not. Let's see if we can get it from the condition of orthonormality. So first of all, what we can say is, if I take an element of the set and I do the inner product with the 0 vector, Joel, you asked for a hard question, so here we go. What does that equal to?
Oh, I don't know.
You need to phone a friend?
Yeah, I think.
Can you guys help him out? He's obviously stuck. What is it?
2.
Oh, shit. It's 0.
Yes.
It's 0.
0.1.
It's, oh boy, you guys.
No, it's not when it's 0.
You were nervous that it wasn't 0?
No, that is not even kind of what I said.
Okay. Well, we can't, I can't understand what you're saying when you're talking through a mask, which of course means you can't understand what I'm saying because I'm talking through a mask, but what the hell are we going to do about that? Anyway, okay. Yeah, what was I saying? Oh yeah. Okay, so let's suppose that I am taking the inner product of xj with not just 0, but alpha I xi. Okay? So what I'm doing is I'm starting off with this, and I'm saying if this is 0, then what does that imply? Well, we can clean this up a bit, because the alpha i's are just constants. They can come outside, and then this becomes xj xi. Okay? But that's just going to be, oh, look. Delta ji, which is just going to be alpha j. Okay?
Why is that? Oh, never mind. I'm just thinking it's 0.
Huh?
Never mind.
Okay, so utilizing the inner product, we have proven that if this equals 0, then this also equals 0. Everybody see that? Yes.
This is going back just a touch, but in that definition, if it is not contained in any larger orthonormal set also in the same vector space?
Yes. Okay? Does that make sense to everybody? Pretty straightforward proof.
Wait, I do still have my question. So,
Sure.
wouldn't, like, the inner product of two orthonormal vectors be 0?
The inner product of two orthonormal vectors? Well, it depends, because you could be taking the inner product of a vector with itself.
Okay, so like xi, xj Oh, I see. Okay.
Xi, the inner product of xi, xj, if these are orthonormal, is just delta ij. That's
Yeah.
That's
Okay.
1 if they're the same, and it's 0 if they're different. And that's why this becomes alpha j, because it's 1 if it, j is equal to I, and it's 0 if they're different. So you only get one term out of that sum. Okay? All right. So now, we're going to move a little bit further, and we're going to talk about Bessel's inequality, which will come back in a bit. If xi is a finite orthonormal set in an inner product space, and x is any vector in the space, then x magnitude squared is greater than or equal to the sum over I of alpha I squared, where alpha I equals the inner product of xi with x. And furthermore, the vector x prime, which is x minus the sum over j, alpha j, xj. And I'm going to use a perpendicular line for orthogonal because I'm getting tired of writing that word. I never spell it right, so this is going to be much easier. To each xi. Okay. Wow. It's running out. Okay. So, wait a minute. Hold on. Pause. What's wrong with this? What's wrong with this? Ross! Are you on?
Yes, I am.
What's wrong with this?
I'm sorry, I really can't see.
But you have the notes that I put on the website.
Okay. Yeah, let me just pull them up here real quick. I'm sorry. So sorry. Okay.
2 sausages are in the oven. One of them looks at the other one and says, "Oh man, it's so hot in here." The other one goes, "Holy shit, a talking sausage!" Sorry, okay. All right, don't worry about it, Ross. I'll ask you another question later, but you should have those notes out. You guys didn't think I was very
Yes,
funny.
sorry.
I miss Avery.
Huh?
I miss Avery.
It wasn't Avery's joke. I had that way before Avery.
You know,
Anyway.
typically jokes are supposed to be funny.
That was brutal.
Kick him out. Get him out of here. You should call her to domestic class.
Yeah, I am just, I don't know what to do about that. I don't know what to do about that.
What does the professor do?
Okay, wait a minute. Now, isn't this equal to sum over alpha I squared? I mean, right? X is the sum over I alpha I xi. The xi are orthonormal. So when you take the inner product of itself, these all give you 1, so that just gives you alpha I squared, and then you sum over them. What is this shit?
I mean, it's not wrong.
Is it not wrong? Well, I mean,
It includes the equal there.
it does include the equal, but what here?
I think I can answer the question. I found where it is in the notes, so I can take a shot.
Okay,
Oh, the reason is because that the vectors alpha I don't necessarily span the space.
now you're
And so
you're
therefore-
cheating, Ross. You're reading further through the notes. I haven't put that up on the board yet. Yeah, don't worry, Ross. I'm going to say that right now, and then I'm going to come back and ask you another question later. Okay?
Okay.
Okay, good.
Sorry.
Yeah, so anyway, the resolution of this is in the notes, which he has in front of him and he's reading. But anyway, the point is this is not a complete set. This is just an orthonormal set. I didn't say anything about it being complete. Okay? Obviously, if it's an incomplete set, then this is not going to hold. All right? So what we can say is the following. The vector x, actually I got it here, the vector x, if this is incomplete, is the sum over these basis vectors, but it would also include a set of the remaining basis vectors that are missing from that set. Okay, so this guy completely spans the space, and x is a vector in the space. Okay? Now, what we can say is the following, and I'm going to call this right here x prime. What we can say is xi x prime equals xi. Now, if x prime is the additional basis linear combination that you need in order to completely formulate x, then you can of course say that x prime is x minus that. So then this is going to become xi, the inner product of xi with x, minus the inner product of xi with sum over j, alpha j, xj. Okay? Well, that's just going to be xix minus pulling out the alpha constants. All right? And then as we said before, this is going to be delta ij, which is going to render that into an alpha I. And this is going to give me alpha I minus alpha I, which is of course 0. What did that just demonstrate?
That xi and x prime are normal.
Yeah, it just demonstrated the furthermore. Okay? We on board? You sure? All right. Okay. Now, what I'm going to do is I'm going to take the definition of a complete basis and I'm going to fashion it into many different statements which are all equivalent. Okay, here we go. So, when do we know if our set X is an orthonormal basis of V? Any of these will work. 1, if X is complete. Okay, that should hopefully be obvious by our previous definition of complete. If xi x equals 0 for all I imposes that the vector x equals 0. If X spans the space. That is, every vector is a linear combination of elements of X. 4. If X is on the vector space V, then X is the sum over I of the inner product of the bases xi, X times the basis xi, summed over all of the bases. If x, y are both on V, then y, x equals sum over y, xi, x, and this is also known as Parseval's inequality. Or sorry, not Parseval's inequality, it's Parseval's equation. And then last but not least, 6. If x is contained on V, then the magnitude of x squared is the sum over I alpha I squared.
Question.
Yeah.
Is X a set?
X is a set, yes. So x,
Set of vectors?
okay, whereas x here is a vector. So x is capitalized. These x's are lowercase.
Oh, okay.
Okay.
Gotcha.
What is this a list of?
This is a list of all of these are statements which can be used to determine whether or not an orthonormal set is complete or not,
Okay.
whether or not it spans a space. Okay? Obviously, these two statements are kind of obvious, but we're going to go through all of them. Okay? Now, I'm not going to prove them. Okay, the proofs are in the book. But rather I'm going to give you examples, because I think examples give you a little more intuition about what's going on. But one thing I want to say about the proofs is that the proofs make use of A implies B. Okay, that's the statement that you're trying to prove, but what the proof does is it uses reverse, that if it's not B, that implies that it's not A. So just let me give you an example. So X is blue implies that X is a color, right? Pretty simple, okay? However, does that mean that if Y is a color, then Y is blue? No. Rather, if Y, so that's wrong. If Y is not contained on colors, then Y is not blue. Everybody agree with that? Okay. So you have to reverse the order of the assignment when you're using the negatory. Okay, that's part of the proofs in the book. I'm not going to worry about the proofs of these. Rather, I'm just going to use an example. Okay? So imagine that we have a vector space, which is R3, but the set of bases that we have is only this x1, x2. Okay? So these are going to be orthogonal, and they'll also be orthogonal to this guy. Okay? This is not a third element of the basis. The set is only going to include x1 and x2. So we want to show how this fails all of these. Okay? That's what I want to show, because this is not a complete basis. Now some of these are obvious. For example, for the first one, so we'll just go through them in order. For the first one, x1, x2. Now remember the definition of completeness? Ross, remind me what completeness means.
Completeness means that the basis spans the space.
No. What does the completeness mean?
Completeness means that every vector in the space can be expressed in terms of the basis.
No. Remind me what completeness means. Throw in the definition.
Well, those are that's the definition of completeness.
Can anybody help him with the definition of completeness? Yes.
That orthonormal set cannot be contained in a larger orthonormal set?
Yes, thank you. That the orthonormal set you're dealing with cannot be contained in a larger orthonormal set. That's our definition of completeness. You got to be a little bit careful, right? Because it's easy to say that completeness is equal to spanning, but those actually are different concepts. Okay? So, is this actually a part of a larger set? Well, it is, because if I call this vector x, no, I'm going to call it y. Then the basis x1, x2 is actually a subgroup or a subset of this larger orthonormal basis. Therefore, this is not complete. Okay? 2. If I take y and I do the inner product with x1, what do I get? And I'll ask a person. Danny, what do I get?
Well, you're going to get 0.
0. Yeah, this is an easy one. What about y with x2? Danny?
You're going to get 0 again.
That's why I wrote it down. That's so easy. But we want to prove that this is not a complete set, or that this is, yeah, it's not a complete basis. So looking at 2. So the inner product with all the elements of the set we're dealing with is 0. However, what can you tell me about y? According to the picture. Say it louder. Y is not 0. Okay? Everybody see this? If having the inner product with the bases giving you 0 forced the vector to be 0, then the set would be complete. But it's not complete, therefore it doesn't force the vector to be 0. Okay? 3. Is that true? No, hell no. Okay? Well, we know that if you have a basis spanning a space, then any vector can be written as a linear combination of that set. Well, this obviously can't happen. Okay? Everybody on board?
Is that a Y or a V?
Oh, sorry, this is a y.
Okay, sorry, thank you.
Sorry, this is y, the vector y. That's this guy right here. What do you think it was, a v?
Yeah, I thought it
No,
might be.
v's look like this. Every time I draw a v, it looks like this.
I don't know about that.
Every time?
Yeah, it's something in my writing. You might notice I never have to write the letter V. But whenever I do, it always looks like this.
You have to keep doing that forever now.
Well,
Oh God, oh yeah, so I think I'm gonna quit. Too goddamn many V's. Okay, maybe a Q, or F, no, not X, God, no, no. Maybe Q. Anyway, yeah, that's a Y. I think it's a Y, I don't remember. Yeah, it's a Y, it's a Y. Damn, it's a Y. Okay, so, sorry. 4, if X is on B, then X, oh, okay, yeah, let's check this out. Y equals x1y times the basis x1 plus x2y times the basis x2.
That should be 0.
That is 0, because each of these is 0. Is 0 equal to y? No. Okay? So that's not true. All right? And then 5. Now I gotta bother you, and I've decided to do it in blue, because blue is the sucky color. Now blue is totally unused. I'm gonna throw in an extra vector, and I'm just gonna call it x. But if we take the inner product of x with y, then this is equal to the inner product of x.
This is some pro gamer shit right here.
I'm pretty good at this.
Oh my god.
What? I don't understand you kids.
Maybe that is right. I don't either.
Take your applause. All right.
I don't even know which.
I know, it's so much fun. Wait a minute, hold on. What's this equal to? And I'm gonna ask somebody through the cards, so don't blurt it out if you know. Oh, shoot. Andrew! It's equal to 0. Why is it equal to 0? Why is it equal to 0? What is this equal to?
0, right?
Yeah, this
That's
is
what
equal
I
to
said. You know, just look at it.
yeah, this is
Yeah.
0, this is 0.
That's what I said.
But is the inner product of x and y equal to 0?
Oh, no.
No. I mean, this is just some arbitrary angle that's not 90 degrees. Okay? Everybody follow? All right, and then last but not least, 6. Remember Bessel.
Is that?
Okay? So remember Bessel's inequality? It's exactly the not equal with the greater than, okay, if you're not dealing with a complete basis. Okay. So hopefully these sort of counterexamples are illustrating the difference in all of these arguments. I mean, what is the difference between complete spans? Well, it's whether or not the set is part of a larger set, and spanning is whether or not every vector can do it as a linear combination. Okay, those are different mechanisms. Okay? Any questions about this before I move on? Excellent. Okay. Oh. All right, one more quick statement, and then we move on to what many of you were probably fearing. All right, so I'm going to finish up with Schwartz's inequality. And this says, for vectors x and y in an inner product space, obviously, because I'm going to use an inner product, the magnitude of the inner product of x and y is less than or equal to the magnitude of x times the magnitude of y. Okay? The magnitude here is just needed because the inner product of x and y could be negative, okay? Whereas the magnitudes of x and y individually are positive, okay? So, let's just prove this really quickly, and this is Swatches Inequality. All right, to prove this, we can say if y equals 0, then what's the left side?
0.
What's the right side?
0.
Ah, that sounds good, yeah. All right, now, if y is not 0, now you might wonder, why the hell did you do that? Well, if y is not 0, then we can form y over the magnitude of y, which by itself, I'm only considering this vector, that's an orthonormal set. It's almost lame, right? And it's only one vector. The only thing you can take the inner product with is itself, but it's normalized, so it's orthonormal. Perpendicular to what, I don't know, okay? And now, we can use Bessel's inequality. We have that x is greater than or equal to the magnitude of y over y x squared. Okay? Everybody on board?
No.
Okay.
Why get
Sorry.
squared?
Huh?
Why get squared?
Just equal to 1, 2.
Because it wasn't squared in the original inequality.
That's true.
So why is it squared now?
Hold on a second.
That's why you have so many questions.
Don't worry about it.
To be bullied.
Yes. No, it shouldn't be squared. Yeah.
It's not,
Huh?
so it's actually just not squared?
Yeah. I don't know why I squared in my notes. I think I went crazy with the twos. Me and the twos, sometimes we get along really well. Okay,
What does that intuitively mean? So, like, I guess if we were gonna look at like three-dimensional space, it'd be the length of some vector is greater than its projection onto a unit vector.
so remember, we're starting out with a set which only has one element in it. And this could be in a space with more than one element in the basis set.
Yeah.
Okay, if it's the only element of the basis set, then any x is just a number times this.
Yeah.
Okay, but we're talking about this being one element in a set which might contain more. Therefore, this inner product is going to be non-trivial. Okay. Now, all you have to do is pull this guy out. Oh yeah, that's right. I'm moving which side things are on. And we get Schwarz's inequality.
Oh.
You just flipped around x and y, like, I thought you could just, I guess it's magnitude.
Yeah, these are the magnitudes, and
Alright.
those commute. These don't commute except they're in a magnitude bars, so they would commute. Or the magnitudes of them would commute if you swap the y and x. Okay?
Okay.
Because this magnitude of y is just a constant. You can pull it out and move it to the other side.
Okay.
Okay? All right. Yes. Okay. Here we go. Now, this is the thing that some of you have probably been anticipating in all hatred, but we're going to do it. Because it is the machine that makes things hum. We are now going to learn how to take a non-orthogonal basis and turn it into an orthonormal basis. Through what procedure? The Gramschmidt, exactly.
So in other words, it's time to go home now?
Yeah, you can go home if you know about Gramschmidt. Okay? So here we go. Let me get us through the Gramschmidt procedure. All right. Okay. So I'm going to apply this to the example of P2. First of all, we know this is not an orthogonal basis, right? Okay, using the inner product, that x, y is the integral from 0 to 1 of x as a function of t, y as a function of t dt. Okay? So now what we would like to do is we would like to take this set, all right, and from it build an orthonormal basis. And this is a very nice methodical procedure. Here we go. So we're going to start by taking, okay, so orthonormal. So the non-orthogonal basis will be basis x, and the orthonormal basis will be basis y. So any y is going to ultimately be an element of the orthonormal basis. So we can start with any vector we want, because if I'm only dealing with one vector, that's orthonormal, as long as it's normalized, okay? So we're going to start our building procedure via taking the 0th element of the set x and dividing it by its magnitude, and Madison is going to be happy to tell me what the value of this is.
The value of it?
Yep.
Like 1?
Yes. I'm taking the number 1 and I'm dividing it by the number 1. Yeah, it's some tricky shit, dude. It's really wickedly tricky. Okay? Now, then what we can do is we can say, okay, y1 is going to be x1 minus alpha 0, y0 over the magnitude of this. Where the alpha 0 in here is to be found. Okay? So what we're going to do is we're going to take the second element of the set, and we're going to subtract contributions that come from here.
Should that be like x naught over x, like the magnitude of x?
Here,
Yeah.
x naught over the magnitude of x naught. Yes.
Is x naught like, is it the number 1, like the first element of x, or is it like?
Yes,
a
it's
vec-
1.
Okay, like it's, okay.
So to give you an idea, what would the magnitude of, or what would the normalized form of this be?
It kind of seems like it would be t.
T? Who says T?
Would it,
Wouldn't they all be 1?
Wouldn't they all be? Well, you tell me.
like I
Okay?
don't understand.
What is x1 over x1? What is x1? x1 is t. What is the magnitude of x1?
Absolute value?
Absolute value of t? Can I get any help? Yes.
Would you want to do like the inner product
Yeah,
Yeah.
remember what
Okay.
this is? Sorry. No, that's fine. Well, what is x1, x1? Sorry, I don't mean to write that. This is the integral of t squared dt from 0 to 1. Yeah, so this is gonna get, okay? So not all of these are 1. Okay? All right. So, okay, so what can I use to figure out what this constant alpha naught should be? Yes?
You could say y1 inner product with y0 has to equal 0.
Exactly. I want these to be orthogonal. Now, I want them to be orthonormal, but, well, this will actually be orthonormal because I'm already normalizing it. Okay? But I want y, let me just find the order in which I wrote this. Yeah, y0, y1 equals 0. Okay? So let's do that. 1 over the magnitude of x1 minus alpha naught y naught times the following, 1x1 minus alpha naught 1y0. Okay? Because remember, y naught is just the number 1. Okay? What is this equal to?
Would you do the integral one again, or would you just be able,
I love what you're saying.
so the integral one again?
Yes, we're doing the,
And so it would just be the integral of t dt?
wonderful. Okay? I was actually going to try and
Really scary
sell.
look when I said 1/2.
No. I was actually going to try and sell you guys the following story, which is bullshit. Okay, so I'm gonna give you the story, and then we'll go, that's bullshit, and then we'll go back and put in your correction. So first of all, I was going to try and convince you that this is just x1, and that this is just y0, which is of course just 1, so that's 1. Now that just means that x1 is equal to alpha 0. That if x1 is equal to alpha 0 and y0 is 1, then this vector is the 0 vector, which is clearly wrong. Okay, the 0 vector is not part of the orthonormal basis. So the correction goes by exactly what you said. This is 1/2. What is this?
1.
You sure?
y0 is 1.
Yeah, it's 1. Well, remember, you got to do the integral. The integral from 0 to 1 of 1 dt.
Well, I'd also note that a normalized vector into product with itself is 1. But
Yes. So this implies that alpha naught is equal to 1/2. And so now we have the full form of our y1. It's x1 minus 1/2 over the magnitude of x1 minus 1/2. Okay, but x1 is just t, so I don't really need to hide that. Okay. Moreover, this is the magnitude of this. Okay, this is a function, but this is the magnitude, which means overall this is no longer a function, it's a number. Okay? And if you work that out, this is going to give you the square root of 12 times t minus 1/2. Okay? So lo and behold, if I take the inner product of this with the number 1, 0. They're orthogonal. Okay. So rather quickly, I will work through the last basis vector, so we have a full set. So then we have our y2, which is going to be x2 minus alpha 0, y0 minus alpha or plus alpha 1, y1. So again, we want to take this guy and we want to subtract out everything here, leaving something which is orthogonal to those over its magnitude. Okay. But here now we have to assure that the result of this is orthogonal to both of the preceding vectors. So y0 and y2 inner product should be 0. And this implies okay? Well, what is the inner product of 1 and t squared?
1/3.
1/3, thank you. What is the inner product of 1 and 1? Say it again?
1.
It's 1. What is the inner product of 1 and t minus a half?
I think it's 1.5.
What can you tell me about these two vectors?
They're orthogonal.
Well, look at this. This is 1 and t minus a half. It's 0. Okay? So this immediately tells me, oh, wait, then 1/3, alpha naught's 1/3. Okay? So alpha naught equals 1/3. And now we can use that it also has to be orthogonal to y1. And in this case, we're going to have the following.
We get to change alpha naught again? Because wasn't alpha naught 1/2 before? Like, didn't we just do that in the last iteration?
Yeah. This is just an unknown to be found from the conditions. So yeah, no, alpha naught here is totally different than the alpha naught here.
Okay.
I mean, I could call it beta naught if that would make you feel better. Do I need to change it to beta naught?
I guess I just don't know why. Like,
Why?
why you were,
So
like, where would beta naught have come from?
well, no, these are just unknowns that I'm solving for based on enforcing the conditions that
Okay,
these vectors are orthogonal.
gotcha.
Okay.
Okay.
All right. So then for this one, we have root 12 t minus a half inner product with t squared minus 1/3 root 12 t minus a half inner product with 1 minus alpha 1 times 12 times the inner product of t minus a half with t minus a half. Okay? What is this equal to? I don't actually expect you to work it out. This is going to give me root 12 over 12. What is this equal to?
0.
This is equal to 0. Thank you very much. And then what is this equal to? Minus alpha 1 times 12 times 1 over 12. Okay? So alpha 1 is going to end up being
-1.
that's not 1.
Oh.
So this minus alpha 1 is equal to 0. So alpha 1 is equal to 1 over root 12. Okay? And now we can write our y2 vector. Our y2 vector, if I work out what the magnitude is in the denominator, now using the expressions for alpha 0 and alpha 1, becomes square root of 180 times t squared minus t plus 1/6. Okay? So there you go. We now have a basis set that is orthonormal. Via Gramschmidt shit. Okay? You think you're gonna do this on your homework?
I guess,
Yeah, you're gonna do it on your homework. But you can always come back to this part of the lecture video and review it if you don't follow. Yes?
I was gonna ask if there's like a simple way to get like the nth orthogonal.
Well, that's what I'm about to write down.
Ah, cool.
Yeah, it is pretty cool. Now, before I write that down, I just want to point out, is this the only orthonormal basis that you could get from in this space? No. How could you use Gramschmidt to get other orthonormal bases?
You could choose any of the original bases as your original x naught and your original x1s and x2s.
Which you're going to do in your homework. Thank you very much. Yeah, you could have started this off with t instead of with 1. And that would change the resulting basis. Okay? What else could you do?
You could rotate it in any way you want.
Yeah, you could take this and rotate it, okay, so that this basis changes into a different basis. It's still non-orthogonal because a rotation of a non-orthogonal basis is going to retain its non-orthogonality, but you could rotate this basis and then apply Gramschmidt to one of those vectors as your starting point. Okay? Yes?
Sorry, it's kind of like a skateboard here. Where's that square root 12 on the final term come from?
Where did this
Extra beta 1 square root.
Where did this come from?
Yeah, I'm just going to look at the equation. Beta naught minus beta 1 times square root 12. And then the inner product of 1 and 2 minus 1 naught.
Second line from the top.
where the betas are,
The beta is here.
square root 12.
Where did the square root 12 basically come from?
I'm taking the inner product of,
That came from
or
1.
this is beta 1 y1. I'm taking the inner product of 1 with everything here. So I want to take the inner product of 1 with y1, but y1 is root 12t minus a half.
Oh, I missed the root 12 on the second one.
Does that mean you get it? Okay, I couldn't understand what the words coming out of your mouth, but you seem to have the disposition of like, I get it now. Okay, cool. Okay, all right. So, sorry, folks. All right, so that's Gramschmidt, and now let me follow an interesting observation, and that is when I'm figuring out these alphas or betas or whatever. Notice one of my inner products always vanishes, and I'm only using the other one in order to determine the coefficient, okay? So we can actually write up a general term applying this. So in general, what we can say is, if I start with x, and then I'm interested in forming the orthonormal basis from it, then starting with the first one, so I'm going to start with y1 is x1 over the magnitude of x1. Then, in general, the m plus 1 element of the orthonormal basis is given by the m plus 1 element of the starting basis minus the inner product of y1 with x m plus 1 times y1 plus the inner product of y2 with xm plus 1 times y plus 2 plus dot 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 plus the inner product of ym with xm plus 1 times ym all over the magnitude.
That's ym, yn at the end there?
That's so y1, y2, yn. Yeah. No. Well, that's ym. You only go up to the ym.
Yeah, okay.
Okay? All right, if you do this, then you're guaranteed that the inner product of any two of your new basis set is going to be the delta function. So in words, what we can say is the following. We want to pick one vector to start with. Okay, it doesn't matter what vector. Pick any vector in the space you want. And then you want to pick the second vector by subtracting out of it any components it has along the first choice. Okay? And then you normalize it. And then you pick the next vector and you subtract out any components it has along the first two vectors. And then you normalize it, et cetera, et cetera. Okay? All right. Now, one last item. And that is, if we have an orthonormal basis, it turns out this provides us with a nice, clean way of determining the matrix elements associated with a linear transformation. So, for example, imagine that we have a linear transformation of some basis vector. Then this is the sum over the elements of the matrix representation. Okay. And now what we can do with the inner product in hand, and assuming that the x's are orthonormal, is we can say, okay, if I take the inner product of xi with the linear transformation of xj, then this is just going to be xi times the sum over k, ak, j, xk, okay? Which is, of course, just the sum over k, a, k, j times the inner product of xi and xk. But of course, the inner product of two orthonormal basis vectors is
Unless they're the same.
yeah, these are summed over in their entirety, so they're going to go over same values and different values, so I'm giving it delta ik, which is equal to aij. Okay? So what we're saying is, if we take a matrix and we act on a basis vector with it, and we know the result, then we can just take the inner product of that with another basis vector. It could be the same one, it doesn't matter. And the result of that inner product is just the matrix element of A. This only works if you're working with an orthonormal basis. Okay, this part right here only happens if the basis is orthonormal. Okay, let's see an example. So I'm going to use D on P1, where D is the derivative operator. And you might or might not remember that if we work with the basis 1t, which is not orthonormal, then the derivative operator in matrix form comes like that. This is truly the derivative operator on linear polynomials using this basis. We derive this. Okay, so this is correct. I would like to check, though, to see if this works or not. So what we can do is we can say, okay, x1 dx1 should be the value of the matrix d11, okay? Let's see. x1 is, sorry, I'm going to call these, I'm going to call this x1 and this x2. So x1 is 1, and dx1 is 0. The inner product of 1 and 0 is? Hey, it matches. I know, this
doesn't
is,
really like give you anything, it's just a way to check if you have an orthonormal basis. Cause like if you're acting on something with the matrix to get a matrix element, then that doesn't like give you anything new, right?
well, so what I'm trying to show you is that this realization of the matrix elements does not work unless you're working with an orthonormal basis.
Okay.
I haven't got evidence of that yet because I just had an agreement.
Okay.
Okay? But if we do x1 dx2, this is the first second element. x1 is 1, dx2 is 1. The inner product of 1 and 1 is 1. Oh look, first row, second column. Boom, it agrees. This is looking pretty good. So x2 dx1, which should be the d21 element. Well, let's see, that's t. What's dx1?
0.
0. What's the inner product of t with 0?
0.
Boom! It's working out. So then I guess this is just going to be d22.
Just call it 0. We're good. Don't worry about it.
Yeah, t. Hold on. x2 is t. What is dxt?
1.
It's 1.
It's 0, just don't worry about it.
That gives you 1.
It gives you 1/2, which is not that. Okay?
That's not the way.
So clearly this doesn't work because this is a non-orthonormal basis. So let's see what it looks like with an orthonormal basis. So if instead we work with the orthonormal set 1 and √3 times 2t minus 1. This is the same first two orthonormal basis vectors we got from Gramschmitting the P2 a few minutes ago, okay? Except it was written as √12 t minus 1/2. It's the same. Yes?
For like an arbitrary set, how do you know which vectors to index with what index, or does it matter? Because like if you call 1 x2 and t x1, would we get the same matrix out?
So if I called this x1 and this x2?
Yeah.
No, well, I mean, you would permutate or permute the elements of the matrix. But that would be fine though. You could call this x2, you could call, yeah, so you could use the basis t1. Okay, and that would just take d here, and it would turn it into that. Because all you're doing is interchanging 1 and 2 everywhere. Yeah. Okay? So let's check it out. x1 dx1.
Is it the same D?
It's the same d. I'm just using a different basis. So look, I actually
Why
worked.
does it get to be the same D matrix? Like, don't you have to change the matrix so that it works with the new basis?
I'm going to get there.
Okay.
Okay? No, I'm gonna get there, I'm gonna get there. First of all, let's construct the matrix this way, and then I will argue that the result is correct, okay? So x1 is 1, dx1 is,
You're gonna get 0.
2 root 3?
You're gonna get 0.
Oh.
it's 0, okay? All right, so that's my d11. x1 dx2. dx2. The derivative of this with respect to t.
root 3.
It's root 3.
Isn't it 2 root 3?
Yeah, it's 2 root 3.
Okay.
That is?
2 root 3.
It's 2 root 3. And what is this one? dx1? And last but not least, and this is going to work out to be anyone? Any takers?
12.
0.
Oh,
Yeah, work it out. You'll get 0. Okay? That's the D2 too. So my D in this case is just 0, 2 root 3, 0, 0. Okay? Now let's ask, is this the correct form of the matrix for the derivative in this basis? So what we can say is, okay, if I'm taking D, if I want to act on a vector, sorry, not, yeah, these should be 1s and 2s. Okay? Then this is the D of alpha 1 plus alpha 2 times root 3, 2t minus 1. D alpha 1 is 0. D times this thing is, or D acting on this thing is, yeah, plus 2 root 3 alpha 2. Well, as a matrix, what this is saying is that if I act on a vector with coefficients alpha 1 and alpha 2, then the derivative is just 2 root 3 alpha 1, or sorry, alpha 2, 0. Which is exactly what this matrix does. Everybody follow? All right, are there any questions? Okay, let's tie it up there. I strongly encourage you to work the homework as it's put out. Partly because if you wait till the last day to work on your homework, it might not be obvious what lecture material the problems are from, but I have already put up 2 homework questions associated with the last lecture, and I'm going to put up 2 more questions tonight based on this material, and then I'll put up 2 more based on Tuesday's material, okay, so that we'll have a quiz on Thursday. But it's just better for you to kind of go along rather than just wait till the very end. So do it.